Hi, in this video, we're going to take a look at the project that you're going to be doing. I'm going to share the screen here. So here we go. This is an introduction to the electric coding project. Before I get into it, I had some kids even earlier today who, groaned immediately when I told them about a coding project. And the thing about it is that I don't care if you don't like to code right now. The thing is that you might feel like you're never going to do anything with computers, never going to do anything with coding, but it's a very computerized world. Even and I say this with somebody who has quite a bit of experience with people who don't want to code. When I was a lot younger, my sister, when she was in high school, had declared that she was never going to do anything with computers. She was never going to work with them. And then she went on to be in charge of the network for a place that she worked, and she's a dance choreographer. She also used programming to control the lighting and sound for performances that she was choreographing. So just because you think that you're not going into computer science, which many of you probably are not, doesn't mean that you're not going to find places or ways to leverage an understanding of how computers work and how to do coding to advance your career in almost any field that you can imagine being in. So I don't think that you should decide today that you are never going to use programming in your entire life. I think that there's a pretty good chance that if you want to be, highly successful in advance, that coding or some knowledge of coding could help you with that. So that's one of my goals with this, is just to give you some more exposure to it. You might not love it, you might not like it, but if you have some idea of how it works, it can give you a sense when a problem does come up that you want to find a solution to, of how using coding could maybe help you get to that solution. So let's take a look at the project. All right, so right now there's three major parts to this project: the basic tier, medium tier, and master tier. I might change these percentages, particularly if I'm not here a lot, because I won't be able to help you much. So the first thing that we will do, we can read this off, but if we actually go here, we'll get a lot more information. So I'm going to go over to here. To get to Trinket, you can just go to Trinket and then log in through Clever. That seems to be the most effective way. So say when you go to log into Trinket, just say that you want to log in through Clever. You're going to see, if you scroll down a little bit, you'll see something called first year physics. So I'm actually going to go over to that so you can see. So you scroll down a little bit, you'll probably only have one thing under my courses, and it'll be that first year physics. When you pop that up, it brings up the template. So this is something that I put together to just try to help you get a sense of what's going on. I'm going to go ahead and make this full screen just for a moment. And I can, of course, change the font size and anything like that if I want to. I'm going to go small because it's on the screen. You can read this, maybe, hopefully. So you can see that what I have now, I've got two balls. This white ball, the one that's moving, is referred to in all of my code as the pith ball. So we've worked with pith before. It's lightweight, it moves. And this other one is what I refer to as the fixed ball. So that one is not going to move. It's not affected by anything else that's happening. And I've got this ball that's bouncing up and down. I can change what it does. I can make it so that it goes like, maybe it's not quite as, actually, that's like almost nothing is happening, right? It's just barely wiggling. Or I can make it so that it, instead of being repulsive, I can make it so that it's attractive. And notice that my program very quickly stopped. So I've got this thing down here that says like, oh no, the pith ball's gone forever, because it went below the other ball, and I don't want that to happen. So I stopped the program. And that's one of the things we're going to be looking at with this set of coding challenges, is how can we make different things happen depending on what's happening in the code. So we'll set up all the forces, all the physics, but then if it does something that we don't want it to do, how do we just stop? Okay, we don't have to let it just run forever. So I'm going to come back to this. Before I dive into the new coding parts and also a quick review of the stuff that you've already done stuff with in the past, I'm going to show you what we have here. So first of all, we're going to be using if statements. This is a little bit of a brief tutorial into how to use if statements. I recommend that you read it, maybe even before you get started with your coding. If statements generally are just a conditional statement that if the condition is met, you then tell the computer to do something else. So I have a very brief example here, like maybe you're setting an alarm and you're programming an alarm into your computer and you want the alarm to go off at 6 a.m. on Wednesdays only. So we do an if statement. We say, if the day is equal to Wednesday, set the alarm time to 6. Okay, and this is how it needs to be structured in order for it to work. If we have more complicated stuff, we can make it more complicated. If we want different things happening on different days, we make that happen, okay? So the basic idea is if something is true, then do this other thing, okay? Sometimes when something is true, we actually just want the program to stop. And that's where a break comes in. So if a condition that you don't like is happening, you can simply tell it to stop by using the break. And so you can see I've got some code examples down here where it shows you, the break will go in here and it'll just stop the whole process from continuing. Once that condition is met, it stops the program from running. So the breaks are going to be inside of loops and inside of if statements a lot of times. All right, so what you're going to be doing, right now I've got the basic tier, which is worth 60%. And in that example, you saw that the pith ball was above the fixed ball. We're going to flip that around so that the pith ball is below. It's actually not going to do this, okay? Because at best, it's going to be attracted upward by this charge and pulled down by gravity. And the force will be stronger the closer it is. So if it's close enough that the field is stronger from electricity, it's just going to always go up. It's not going to bounce down and fall because of gravity. Likewise, if it's a little bit further away, gravity is stronger than the field because the electric field gets weaker as you get further away. So it'll just fall forever. So it's a little bit different. It's not going to bounce around. It's just going to rise or it's going to fall. It's not going to do both. All right. So what your task is going to be is to, first of all, make it so that the pith ball goes from being above to being below. Set its position to be lower. Okay. You're going to then have some if statements that are just going to indicate whether the ball is going up. And if it's going up, you want to print that out. And if it's going down, you want to print that out. And then we're going to break the whole program, tell it to stop, if the pith ball ever gets above the fixed ball. Okay, so that's going to be another if statement to help us see if that condition is met. I then have a bunch of tips. I would recommend that you read the tips before you even get started, okay? Because it gives you some advice. If you don't follow these tips, you're probably going to end up with a program that's not doing what you expect it to do. So read through. It's really important, especially without me here to help you, that you read through stuff. Medium tier. Now you're going to add another fixed ball. So you're going to add two fixed balls, have them side to side, and you're going to have the pith ball oscillate between them. It can oscillate vertically or horizontally. So I just show you what I mean by that. So that's vertical oscillation, and this is a horizontal oscillation. You only need to do one of these if you want to get that higher grade. And again, it goes through what you need to do, and then some tips for making that all happen. And finally, if you want the 100%, there's two options, which I'll mostly let you read through on your own because I want to keep this as short as possible. This is an example of what one of those options might look like ultimately, where I've got like 4 fixed balls, and this one is kind of oscillating in there. So let's go back to the template, because for a lot of this, you're going to be able to do a lot of copying and pasting so that you're not starting from scratch. You're just kind of modifying some things, especially for the basic tier, and even quite a bit for the medium tier. So a couple things. I'll go through this and I'll help you get started a little bit. So I'm going to make this full screen. All right. I put comments. I would read the comments, okay? These are just giving me the size of the charges. This is telling me how far apart I want them initially. So what is their initial separation? And this is making gravity. So this is making the gravitational acceleration. It's 9.8. And then remember that when we're doing this, we're often talking about vectors. So vectors tell us that things are happening in a particular direction. They're not just a size, they have a direction. And the direction for gravity is down. So this is the X direction. This is the Y direction. That's the Z direction. I want this to go down in the Y direction. So that's -1 there. All right, you don't have to touch this. This is just making the screen show up. I will point out that we're talking about a range. of 3 centimeters. So we're really, really zoomed in on what's happening. So this whole window over here is representing 6 centimeters total in each direction. But you really shouldn't need to change that. All right, so the next thing I need to do is make the balls. This should seem kind of familiar because we did this before when we did the planetary simulations. And there's a reason why I'm doing this project now, because it has a lot of similarities with that planetary simulation that we did. So we got it the pith ball. We need to make it a sphere. So that's our code here. And then the sphere has lots of properties. For instance, where is it? So that's the position. And I'm setting the pith ball just that separation distance above 0. I tell us how big it is. It's pretty small. And that's like a millimeter radius. I set the color, and you can play with those numbers if you like. I gave it 0 velocity acceleration to start. Gave it a really small mass. It's a pith ball, so it's basically a gram is what I said it was here. And then I set it to whatever charge it is here. That makes it easier for me to change this just by focusing on the top. I don't have to scroll down to change stuff. And then I make my fixed ball, and I can actually what I did was I just copied and pasted this part right here, and I just changed a couple things. And then you'll notice that this time I have arrows. I didn't have arrows when we did the gravity stuff. Arrows are just another shape, just like a sphere. So I just make another shape. The position I want to be located at the pith ball, because these are the forces that are acting on the pith ball. Unlike a ball, though, arrows have direction. So I want the direction of the electric field arrow I made it default actually upwards, and I made the gravity one default downwards. Right now, this doesn't really matter. This is all going to change when we start doing calculations. All right. You don't need to really change this stuff for the most part, other than maybe the axis part. But you'll see how the calculations work later. And then I added one more thing, which is a graph. You don't need to really change this at all. If you want to change the color, cool, but you don't need to change anything else. Lastly, set up the Coulomb's constant. I set my initial time to 0. This is the time step. So this is the time between calculations. So I've set it to be 1/1000th of a second. So every 1/1000th of a second, we're going to recalculate what's happening and update that on the screen. And then I'm going to let it run for 1 second. You could change this, but 1 second is good enough to kind of see what's going on. All right, so that's all the setup stuff. I made my shapes. I made my arrows. I made my graph. Now I'm ready to do calculations. So we're going in the while loop here. And in the while loop, what I'm saying is that we'll keep running these calculations as long as the time is less than the maximum time that I set. You probably don't need to touch this, but this is how rapidly it shows you the calculation results on the screen. So if it's kind of going slow, you can always increase this number by a bit. When we're doing Coulomb's law, we need to know how far apart, the charges are from each other. So that's all that this is finding. It's finding how far apart and in what direction they are. So I'm going to actually try to share my smooth draw. Where is smooth draw? Okay, so here's smooth draw. Yeah, so this is our equation. K Q1 Q2 over R squared. That's going to tell us force between two things. What I want to point out here is that if I've got two charges, my R direction, say this way, is also in the same direction that the force will be if both charges are the same sign. So if I'm looking at this, if these are both positive charges, then if R is this way, the force will be this way on this charge. If they're opposite signs, then the force will be in the opposite direction, but that'll be taken care of by one of these being positive and one being negative. So the way that I'm going to write this in the code is I'm going to write it like R over R cubed. I can't really deal with vectors if I'm raising things to different powers. So what I want to do is I just want to have the R vector here, just on its own. And then that's the same as this, as long as I divide it by R cubed. So this is telling me the direction that my force will go. If one of these is negative, then it flips the direction of the force. If they're both negative, then it flips the direction of the force again to be repulsive. Okay. So I'm going to actually go back, and then I'll come back again. So that's located right here where I calculate the force between them. And you can see that I've got the K, charge 1, charge 2, times R, and then divided by the size of R cubed. One weird thing about Python is that when you raise things to a power, you don't use the caret, you use 2 asterisks. To find the acceleration, I need to take the sum of forces, which in this case is gravity and the electrostatic force, and divide by the mass. To get the new velocity, I set it equal to the old velocity plus the change in the velocity, which I can calculate with acceleration times the time. So I'm going to flip back over to here for a second. We have an equation from the beginning of the year, acceleration equals change in velocity over change in time. I can rewrite this and just do some rearranging. So delta V is V minus V initial. I can multiply both sides by T. And then I get that the new velocity is equal to the old velocity plus however much the velocity has changed due to the acceleration over that small amount of time. So that's all that this line of code is doing. And this does a similar thing. The new velocity equals the old velocity times the change, the new position equals the old position times the change in the position, which we can calculate by taking the velocity times the change in time. All right, arrows. First of all, I update the arrow's position to match where the pith ball is because the pith ball is moving, so I need the arrows to move. The axis needs to line up with the direction of the force. So if I'm talking about the electric arrow, I want it to match the direction of the electric force. One way that I can do that, because all of my motion is going to be vertical here, I don't need to worry about X or Z. I can just focus on the Y direction. So I said, you know what? I can just look at what direction my force is in and then multiply that by a vertical vector. So if the electrostatic force is up, I get an up arrow. If the electrostatic force is down, it flips the direction of that vector to be down. And I do the same thing with gravity. And then for my graph, you don't really need to change this at all, most of this. If you want to graph a different thing, you could graph it here. So the graph plot part stays the same. This is the x-axis, this is the y-axis. So I'm just graphing the y position because that's the only thing that's really changing. I could do this, I could do something with the velocity if I wanted to, or acceleration as well. All right, so now we get to the brand new stuff, which is if statements. All right, so this could go wrong. This program could go wrong in a couple of ways. First of all, I think that if it goes below the pith ball, I should just stop the program for the most part. So I said, if the pith ball's position in the y direction is less than the fixed ball's position, and it's accelerating downwards, we're pretty much done. So I say, oh no, the pith ball is gone forever, and I break it. That's because if it's below the pith ball and it's still falling down, it's not attracted back up, you're not getting that pith ball back. If it was like accelerating upwards, even though it's below the ball, then it's going to slow down and oscillate back up, and I'm going to let that run. But if it's going downwards and the electric force is just so weak that gravity is just going to keep pulling it down, I'm stopping the program. Okay, so that's what's happening here. So I write my print statement so that I can see the result. And I break it so that it just stops running. I don't have to watch this thing go on forever. And then I say else if, and in Python, instead of writing else if, we just write elif. It's just an abbreviation. So what we have then is, if this is true, do this. If it's not true, check to see if this other thing is true. And the other thing here is if the acceleration in the y direction is greater than like 300 times gravity, meaning it's being rocketed up at like incredible accelerations, we're just stopping because that thing's gone. It's not coming back in a second. So our force, electrostatic repulsion force, was too big. It's over. We're breaking it. If neither of these things is true, then we just go on. We just keep running the rest of the calculations. And our final calculation is always to just update the time so that this program does eventually end. So that's t equals t plus delta t. So the new time equals the old time plus the change in time. And that's this code. When you do the basic level, you're going to be changing where this is located. So instead of maybe having a separation position that's above the fixed ball, you're going to go below. I also, in the notes, in the tips, say get rid of these if statements. You're going to have to make your own, but these if statements don't work if we change where the ball starts. So get rid of them and start over. You can always go back and refer to them, okay? So I'm just gonna show you how to get started on that next one. So we can go over here, right? We see all this stuff, it's great. We kind of have an idea what to do. I'm gonna go back here. And to make a new trinket, you're gonna go make a new trinket. And we are using Glow script, okay? I would recommend that you right click and open this in a new window. And then just copy and paste all of this into there. Okay, so just, you can get rid of this because we're just copying and pasting the whole thing. Okay, so it'll go in there. And then just make the changes you need, title it, run it, save it. And then when you're done, it'll give you an option to share a link, share the link and submit it in Canvas, and then move on to the next project. Okay, so that's the basic idea. Hopefully this helps you get started. I'm sorry, I'm not there. That'll be it.